Hey everybody, so I'm putting together this screencast to contrast the metric system with the British gravitational system, and we'll be talking about dimensions and units in both of those, and I'll discuss some conversion issues that we've got with the British gravitational system, and you'll want to learn how to work with those, even though it makes your life a pain. But if we look at the metric system first and think of the dimensions of mass, length, time, and force and their respective units. In the metric system, we've got units of kilograms for the dimensions of mass. For the dimensions of length, we've got meters. For the dimension of time, we've got seconds. And for the dimension of force, we've got newtons. In the British gravitational system, on the other hand, we see things like for the dimensions of mass, we'll see pound mass. For dimensions of length, we've got feet. Time, again, is seconds. And for the force, we've got pound force. And when you work with this system, it's really important to distinguish between pound mass and pound force. So if we go back and look at the metric system, we want to be able to relate the force, the dimensions of force to the dimensions of mass, length, and time. And in the metric system, it's really simple. We all know now that 1 Newton is simply equal to 1 kilogram meter per second squared. In the British gravitational system, however, how do we relate the dimensions of mass, length, time with the dimensions of force? So let's look at this. We got the dimensions of force. We've got 1 pound force. How do we relate this to the basic units of mass, length, and time? So we've got pound mass, feet per second squared. And what makes our life tricky, a little bit weird to work with, is the fact that when you look over here in the metric system, 1 Newton is equal to 1 kilogram meter per second squared. However, in this system, we've got 1 pound force is not equal to 1 pound mass foot per second squared. And as it turns out, 1 pound force is actually equal to about 32.2 pound mass feet per second squared. So the fact that this isn't 1 makes our life a pain. And if we look at the way the two systems are defined, we find for the metric system that a force of 1 Newton will accelerate a 1 kilogram mass at a rate of 1 meter per second squared. So let's put a little mass here, and this little ball weighs 1 kilogram. And we're going to apply a force to it of 1 Newton. And it turns out that 1 Newton applied to a 1 kilogram mass will cause it to accelerate at this rate of 1 meter per second squared. And that simply arises from the fact that F equals ma, and if we've got a force, let's say we've got a force of, or actually let's solve for the acceleration. So the acceleration is a force divided by the mass. And if we've got a force of 1 Newton and a mass of 1 kilogram, if we use this identity, or this definition in the metric system, we can break newtons out into kilogram meters per second squared. So let's do that. So we've got 1 kilogram meter per second squared, and in the denominator we've got 1 kilogram. So doing the math, the kilograms fall out, and we're left with 1 meter per second squared. And then we say, well, all right, let's do the same thing for the British gravitational system. So now we've got, instead of our base units of kilograms, we've got a base unit of pound mass. So let's draw this. We've got another object, another sphere, and this thing weighs 1 pound mass. And let's apply a force. Our basic dimension of force is pound force. So onto this object, we're going to apply 1 pound force to it, and we're going to see what happens. And we draw the arrow to the right, and we're going to figure out what is A going to equal. So again, we've got F equals ma, and solving for acceleration, we've got F over m. And we say, all right, so we've got a force of 1 pound force divided by a mass. We're going to use our base units of pound mass. And you look at this thing and you say, I don't know, I've got dimension that I've got pounds over pounds. What do we do with this? And the fundamental difference between these two systems is that in this case in a metric system we're defining 1 Newton based on our definitions of kilograms, meters, and seconds squared. So it's real simple. We've got, all right, 1 kilogram meter per second squared. We're going to define a Newton around these quantities. In this system, it's a little bit backwards, though. Like they'll start, they defined it as, they start with 1 pound force, and they've defined 1 pound mass in terms of 1 pound force and a length of feet in a time of seconds. So that's where things get a little bit backwards, and we have to use this conversion of 32.2. So if you take anything away from this, just know that 1 pound force does not equal 1 pound mass. But in this system, if we want to do something similar to what we did in the metric system, we have to use this conversion. We've got 32.17 pound mass foot per second squared per pound force. So now we finally got a way to do something similar to what we did with the metric system. We can make our dimensions of mass fall out of the equation, and we can come up with something that makes a little bit more sense in terms of acceleration. So in this case, the pound mass will cancel out. Our pound force will cancel out because of a conversion factor, and what we're left with is foot per second squared. Acceleration equals 32.17 feet per second squared. So in the British gravitational system, we might also see mass defined, the dimensions or the units of mass defined as a slug. And the slug, you think, well, all right, what's a slug? And if we go back down, we'll look at this definition of the dimensions of mass versus these units describing the dimensions of mass. So think about pound mass versus slugs. So we think, all right, let's think of it this way. Let's think of it in terms of slugs and feet and seconds. So I'm going to draw the same object again, except this time I'm going to say the object has a mass of 1 slug. And to this slug, we're going to apply a force of 1 pound force. And in this case, we want to figure out what is the acceleration of this object. So the acceleration, again, is equal to F over m. And we're going to apply a force of 1 pound force, and the mass of this thing is 1 slug. So how do we get these weird units in terms of acceleration? What we want is something in terms of a foot per second squared. And it turns out that 1 slug is defined in this manner, where we've got 1 pound force. Let's erase that. We got 1 pound force is equal to 1 slug foot per second squared. So if we make this conversion, we'll substitute this into here. We've got 1 pound force is equal, and we're going to divide by the mass of 1 slug. And turns out slugs will fall out, and we're left with 1 foot per second squared. So the acceleration in this case, in these units, we've got an object with a mass of 1 slug, and we're going to apply a force of 1 pound force. And it turns out in this case, conveniently enough, that we've got the acceleration of 1 foot per second squared. So I hope this short video emphasized why working with the metric system makes our life so much easier. And if you take one thing away from this video, remember that 1 pound force does not equal 1 pound mass. And the conversion factor that you need to remember is that 1 pound force is equal to 32.17 pound mass foot per second squared.